I just used a lot of metaphors to tell you how GAN works. I also told you how you use GAN in practice. Now, we are going to talk about the theory of GAN, and talk about the parts which are not covered in the content farm. Tell you how GAN works. I'll tell you why the interaction between the generator and the discriminator can make the generator generate tons of lifelike human faces. What's the mechanism behind this? First of all, let's figure out what the training goal is. Every time we train a network, we always have to choose a loss function and use gradient descent to update the parameters. We need to minimize loss function. But in this generation problem, what kind of loss function should we minimize or maximize? What is it? We have to figure this out to be able to take a step further. For a generator, what do we want to minimize or maximize? The answer is, given a generator and a lot of vectors randomly sampled from the normal distribution, the generator should output a more complicated distribution. We call this complex distribution PG. Also, we have a bunch of real data. The real data also forms another distribution called P data. We hope that PG and P data can be as close as possible. If you can't imagine what PG and P data are, we use a one-dimensional case to explain first. Suppose that the input of the generator is a one-dimensional vector. The generator's output is a one-dimensional vector, and the real data is also a one-dimensional vector. Then the normal distribution should look like this. Then, we give this vector to the generator. Suppose you enter 5 data points. The location of these data points will change. It will generate a new distribution. Originally, data points were centered in the middle. Then, these data points are divided into 2 groups after passing through a generator. So your distribution becomes like this. In addition, P data refers to the distribution of the real data. The real data distribution may look like this. It's much sharper. And the left side contains more elements. Comparing to the right side, we expect the distribution on the left and the distribution on the right to be as close as possible. We can use a formula to describe this. Divergence of PG and P data means the divergence between PG and P data. What does divergence mean? You can regard it as a certain distance between these two distributions. If this divergence is large, it means that these two distributions are not similar. On the other hand, if the divergence small, it means that the two distributions are close. Divergence is the measure of the similarity between two distributions. Our current goal is going to find a generator. The so-called find a generator actually means find a set of parameters in a generator. Note that the generator is also a network. There are a lot of weights and biases in it. Find a set of generator parameters to generate PG, and the divergence between this PG and P data should be as smaller as possible. What we are looking for is such a generator. We use G star to represent it here. So what we have to do here is actually very similar to what we do when training a normal network. We told you in the first class. We define a loss function and find a set of parameters to minimize the loss function. We have actually defined our loss function now. In this case, our loss function is the divergence of PG and P data. It's the distance between them. The closer they are, the more similar the generated PG and P data are. We hope PG and P data can be as similar as possible. In other words, we want the divergence between PG and P data to be smaller, and we are trying to find a G to minimize the divergence. But we are faced with a difficulty here. The difficulty lies in the calculation of divergence. The loss function is easy to calculate. But how about the divergence? You might have heard of some names, such as KL divergence or JS divergence. If you apply those divergence formulas on continuous distributions, you have to do a very complex integration, which is impractical to do. So it seems impossible to calculate the divergence. Then how do we find a G and minimize divergence if we can't even figure out the divergence? This is the major problem. We will suffer when we try to train the generator. GAN, though, is a powerful method. It can overcome the difficulty of calculating the divergence. So the current problem is that we don't know how to calculate divergence. But actually, As long as you can take samples from the two probability distributions, PG and P data, then you can calculate the divergence. To calculate the divergence, we only need the ability to sample from the two distributions, but not the actual form of them. Is this doable? Fortunately, yes. So how do we create samples of the distribution from the real data? The method is very simple. Just randomly take any stuff from your database, and you can obtain P data. How about the generator? We can generate some sample vectors from the normal distribution and feed them into the generator. I had mentioned before that the distribution we are sampling from should be simple enough to write down the formula and generate samples. That's why we choose the normal distribution, which is obviously capable of what we need. Starting from the vectors sampled from a normal distribution, let the generator generate a bunch of pictures from them. Then we can treat the resulting pictures as samples of PG. Now we have a method to take samples from both PG and P data. GAN then gives us the ability to train the model, while all we can do is creating samples. I don't even know the exact form of PG and P data. With only the ability to sample, we are able to estimate the divergence. We are going to rely on the discriminator to do this. Recall how we trained the discriminator. We have a bunch of real data. That's samples from P data. We also have a bunch of generated data, which can be treated as samples from PG. We are going to train the discriminator with those two datasets. The goal of the discriminator is to give higher scores to real data, but lower scores to generated data. I kept highlighting that. The goal of the discriminator is to distinguish real pictures from generated pictures. When it sees a real picture, the discriminator should give it a higher score. When it sees a generated picture, the discriminator should give it a lower score. We can write down the formulas and think of all the stuff above as an optimization problem. Specifically, we are trying to train a discriminator which maximizes some function. We will call this function the objective function. But if the goal is to minimize the function, we call it loss function. We are now looking for AD, which can maximize this objective function. What is the formula of the objective function? The formula of the objective function looks like this. We have a bunch of y. Follow the distribution of P data. That is, they are real images. We feed these real images to the discriminator to get the logarithm of the output score. What about the other part of this formula? We have a bunch of y. Follow distribution PG, the generator output. We also feed these generated images to the discriminator to get a score. Then compute log of 1 minus d of y. We hope that the value of objective function v as large as possible. We hope that the larger the v, the better. It means we want to make d of y as large as possible. If we sample y from P data, the value of d of y becomes larger and larger. If we sample y from distribution PG, the generator output, the value of 1 minus d of y becomes smaller and smaller. Then we maximize the formula of v. We are going to find a model d to maximize this objective function. We just make d of y the larger and larger. Let d of y, the score of generated images, as small as possible. The smaller the value of discriminator output, the better. This thing is actually equivalent to. You may think this formula is weird at first glance. But the objective function is not necessary to be written in this form. You can write this formula in other ways. There is a reason why it was written like this in 2014. There is a thoughtful reason. There is a thoughtful motivation. The author of GAN believes discriminator has something to do with the classification. Discriminator has something to do with the binary classification. How to say? This objective function is cross entropy multiplied by -1. Our objective in training a classifier is to minimize cross entropy. When we maximize this objective function, maximize cross entropy with a negative sign, is equivalent to minimize cross entropy. It is equivalent to training a classifier. So what the discriminator does, if what discriminator does is to maximize the objective function, discriminator can be viewed as a classifier. The classifier treats these blue dots, samples from P data, as class 1. The classifier treats samples from PG as class 2. There are two classes of data. And train a binary classifier. After training this classifier, it is equivalent to solve the optimization problem V. The most magical thing is the following sentence. This formula, the value in this red box, is related to JS divergence. The interesting thing is, the idea might come from binary classifier. In the most primitive GAN paper, in the beginning, discriminator is written as binary classifier. So we have cross-entropy objective function. After some deduction, the maximum of the objective function, you find AD, can make this objective function reach its maximum. This maximum value is related to JS divergence. They are not exactly the same. The objective function is obviously not designed for JS divergence at first. After some deduction, the author found that they are related. As for the actual derivation process, you can refer to the original paper written by Ian J. Goodfellow. I think the derivation process in the paper is pretty clear. The real magical place is the maximum value of this objective function is related to divergence. Even if we don't know how to count divergence, it's okay. Train your discriminator. After training is finished, see how large its objective function can be. That value is related to divergence. We didn't show the proof to everyone. We can still understand it intuitively. Why the value of this objective function is related to divergence. This intuitive understanding is not very difficult. Because you can think about that. Assuming the divergence between PG and P data is very small. It means that PG is very similar to P data. The difference between them is small. We sample several points from PG and P data. Blue and red stars are mixed. The discriminator is trained as a binary classifier. At the time, for the discriminator, since these two piles of data are mixed, it's hard to separate them. This problem is difficult. Since it is difficult to separate them, we are not likely to have this objective function very large. So the maximum value of V in this objective is relatively small. The small divergence corresponds to the small maximum value in this objective function. It's not the value of the objective function. It is the largest value that the discriminator can be obtained from objective function with exhaustive possibilities. If your two sets of data are very different today, their divergence is very large. For the discriminator, it can easily separate them. When the discriminator can easily separate them, this value of the objective function can be very large. So when you have a large divergence, the maximum value of this objective function can be very large. Here is an intuitive way to tell you. For detailed proof, please refer to the original paper of GAN. Some assumptions are being made inside. For example, the capacity of the discriminator is infinite. After the assumptions, you can get derivation related to JS divergence with this maximum value. Back to the beginning. Our original goal is to find a generator to minimize the divergence between PG and P data. But we are stuck and don't know how to calculate divergence. Now, we know that we only need to train a discriminator. After training it, the maximum value of this objective function is related to this divergence. The maximum value of this objective function is this divergence. Why don't we replace the divergence with the item in the red box? Why don't we replace the divergence with the item in the red box? So we have such an objective function. This objective function is a bit complicated at first glance. There are a minimum and maximum at the same time. So you will turn your head if you are not careful. We are looking for a generator to minimize the function in this red box. But the function in this red box is another optimization problem. It is to find a discriminator with the given generator. This discriminator can maximize the objective function V. Then we find a G to minimize the value in the red box. This G is the generator we want. The generator and discriminator we just talked about interact or deceive each other in this process. In fact, we only want to understand this min-max problem. We solve this problem with the algorithm of GAN we mentioned above. Why the following algorithm can solve this problem? You can see paper of the original GAN. Now, you maybe ask why to use JS divergence. Even it's not really JS divergence. It's just related to JS divergence. Why not use real JS divergence or another divergence? For example, KL divergence. Of course, you can do it. You only need to change the objective function. Then, you can use all kinds of divergence. How to design objective function for different divergence. There is an article called GAN in paper. There are very detailed proofs. There are a lot of tables to tell you how to design objective function for different divergence. Once you design an objective function, its maximum value tells some kinds of divergence. There are detailed records in this article. Some people would ask why the training of GAN is not very easy. It may be we are not the minimized JS divergence. But, after GAN was introduced in this paper, we now have a way to truly minimize JS divergence. However, even if we can minimize JS divergence, the results still leave much to be desired. It's still very hard to train GAN. So, GAN are notoriously hard to train. As the saying goes, no pain, no gain. This goes to show how hard it is to train a GAN. So, we're going to talk about some tips for training a GAN. Since it is very hard to train a GAN, there exist many tips for training a stable GAN. For the sake of time, we'll only talk about the most famous one, and many of you might have heard about it before. Hold on. I need to change my microphone real quick. Alright, this should be fine. Okay, back on topic. Many of you might have heard of GAN. What is GAN? Before we introduce GAN, let's talk about the problems with JS divergence. Initially, when we want to train a GAN, we try to minimize the JS divergence. What's the problem with using the JS divergence? Before we try to solve the JS divergence problem, let's take a look at what features PG and P data have. A key feature of PG and P data is that the overlap between PG and P data is often very small. How come? There are two main reasons. The first reason comes from the nature of the data. If you think about it, PG and P data are used to generate images. And an image is actually a low-dimensional manifold in the high-dimensional space. How do we know that an image is a low-dimensional manifold? Think about it. When we sample a point in a high-dimensional space, it usually can't form an anime avatar. So, in reality, the distribution of anime avatars in the high-dimensional space is actually very narrow. Now we know the distribution of anime avatars is actually a low-dimensional manifold in a high-dimensional space. Alternatively, if we think about it in a two-dimensional space setting, the distribution of the images could be a line in a two-dimensional space. Most data points in the two-dimensional space are not images. Just like how a random data point in high-dimensional space isn't an image. The area that can be sampled to form an image is very small. From this perspective, PG and P data are both low-dimensional manifolds. Judging from the nature of the data, in terms of two-dimensional space, PG and P data are like two straight lines. The area of intersection between two straight lines in the two-dimensional space is almost negligible, unless one line is on top of the other. This is the first reason. Some people might say that an image might not actually be a low-dimensional manifold. If the first reason couldn't convince you, here's a second one. The second reason is that we never actually knew what PG and P data look like. The understanding of the distributions of PG and P data actually came from sampling. So, maybe PG and P data do have a very large overlap. However, when we want to compute the divergence of PG and P data, we have to sample some data points from PG and P data respectively. Since we only sample a limited amount of data points, if the sampled data points are few in number or too sparse, there won't be any overlap between the two in the eyes of the discriminator. Even if the overlap area does indeed exist. For example, in this image, the blue distribution and the red distribution do indeed overlap. However, when we sample some blue dots from the blue distribution and some red dots from the red distribution, we can separate these dots with a curve. Since we sampled few dots, this completely separates the red dots from the blue dots. Thus, we can say that the red dots are on the right-hand side of the curve, and the blue dots are on the left-hand side of the curve. This is totally reasonable. So the above gives you two reasons. Trying to convince you that the two distributions of PG and P data overlap only in a very small region. And what will the fact that there is almost no overlapping affect JS divergence? JS divergence has a feature that the JS divergence of two non-overlapping distributions will always be log 2, no matter what the two distributions are. So as long as the two distributions do not overlap, it must be log 2. No matter what they look like, it's always log 2. For example, assuming this is your P data, and this is your PG, assuming that they are both a straight line, and there is a long distance in the middle, then their JS divergence is log 2. Suppose your PG is quite close to P data. The interval between them is relatively small. The result is still log 2. Unless your PG overlaps with P data. Otherwise, as long as the PG and P data are two straight lines, and the two lines do not intersect, then it's log 2. In this case, it is log 2. In this case, it is still log 2. But obviously, this case is better than this one. The case in the middle, the generator in the middle, is better than the generator on the left. But you don't know. The blue line is closer to the red line. However, from the view of JS divergence, you can't observe such a phenomenon. Since from the view of JS divergence, you can't observe such a phenomenon. When you are training, you simply can't make this kind of generator to be updated to become a generator like this. Because of your loss. For your objective, these two generators are equally good, or they are equally bad. The above is from the perspective of theory. If we explain from the perspective of a more intuitive operation, you will find that when you use JS divergence, you assume that you are training a binary classifier to distinguish between real image and generated image. In fact, you will find that after training, the accuracy is almost 100%. Why? Because there are not many sampled pictures at all. For your discriminator, your 256 sampled real pictures and 256 fake pictures can be separated into two groups easily by cramming up. It knows who is real and who is fake. Therefore, if you have trained a GAN in practice, you will find, if you train it as a binary classifier, you will find that, almost every time you finish training your classifier, that is, your discriminator, the accuracy is always 100%. Originally, we expected that the loss of the discriminator may represent something. This binary classifier loss may represent something. This loss is getting higher and higher, meaning the task is getting harder and harder. It means our generated data are getting closer and closer to real data. In fact, you can't observe this phenomenon in practice. The loss of the binary classifier after training doesn't make any sense at all, because it can always get 100% accuracy. Two groups of images are from sampling. It can easily get 100% accuracy by cramming up. You have no idea whether your generator is getting better and better. In the past, especially when there is no skill like GAN, when we used binary classifier as discriminator, it's really like witchcraft to train a GAN. You don't even know whether your GAN is getting better or not. So, at that time the approach was, every time after you update the generator some epochs, you have to print out the generated picture. Then you can eat something and look at the result of that pictures at the same time. Maybe you would find that it was broken and restart the training. So in the past, you didn't have anything. Unlike when we are training a normal network, you have a loss function. Then the loss will gradually become lower. During the training process, when you see that the loss is becoming lower, you can rest assured that your network is training. Whether it will overfit is another thing. At least it is getting better and better on the training data. But for GAN, originally, we expected that the loss of the classifier could provide some information. But when your classifier is a simple and general binary classifier, you don't get any information from a result of its training. The accuracy is 100% every time you train. You don't even know whether your generator is getting better. You can only see it with human eyes. You see it with human eyes in front of the computer. If you find that the result is not good, you terminate it and use another set of hyperparameters and adjust the network. You reconstruct the network. So training GAN in the past was a bit hard. Since it is a problem of JS divergence, someone may think that changing the way of measuring the similarity of two distributions, changing a kind of divergence, can solve this problem. So there is this, Wasserstein. There's an idea of using the Wasserstein distance. Okay, there is a trivia about the Wasserstein distance. This W here actually pronounces V. It doesn't pronounce W. It's not Wasserstein distance, but Wasserstein distance. Okay, how this Wasserstein distance is calculated? The idea of Wasserstein distance is like this. Suppose you have two distributions. One distribution we call it P. Another distribution we call it Q. To calculate Wasserstein distance, you just imagine you are driving a bulldozer. Bulldozer is called earth mover in English. Imagine you are driving a bulldozer. You think of P as a pile of dirt. You think of Q as the destination where you want to pile the dirt. Then the average distance for this bulldozer to move the soil on the P to Q is Wasserstein distance. In this example, we assume that P is at this point, and Q is at this point. For the bulldozer, assume it wants to move the soil on the side of P to the side of Q. The average distance it has to travel is d. So in this example, assume that P is at one point, and Q is at another point. If the distance between these 2 points is d, then the Wasserstein distance between P and Q is d. When talking about Wasserstein distance, since you have to imagine that there is an earth mover, a bulldozer bulldozing, Wasserstein distance is also called earth mover distance. But if it is a more complex distribution, it's a little difficult to calculate Wasserstein distance. Why? Suppose this is your P, and this is your Q. Assume you drive a bulldozer to reshape P so that the shape of P is closer to Q. What's the way to do it? You will find that your possible moving plans for reshaping P to Q are countless. You can say that I move the soil here to here. I move the soil here to here, turning P into Q. But you can also say that I moved the soil here to here. I moved the soil here to here. Although I choose a farther path, I can still turn P into Q. So when we consider a more complicated distribution, there are so many different methods that can turn P into Q. There are so many different methods. You have a variety of moving plans. The distance you calculate, the average distance your bulldozer travels, is different. In the example on the left, the bulldozer travels less on average. In the example on the right, the bulldozer travels more on average. For the Wasserstein distance between P and Q, will the value be different based on different ways for the bulldozer to travel? In order to make the Wasserstein distance have only one value, the definition of Wasserstein distance here is exhausting all the moving plans to see which bulldozing method, which moving plan, which bulldozing plan could minimize the average distance. The smallest value is the Wasserstein distance. So, the ways to transform P into Q will be exhausted. Then, we can see which bulldozer has the shortest average distance. And we can choose it as the Wasserstein distance. So, actually, to calculate the Wasserstein distance is quite troublesome. You will realize that to calculate only a distance, I have to solve an optimization problem. Once the optimization problem was solved, we could calculate the Wasserstein distance. Okay, let's skip it. How to calculate the Wasserstein distance? Let's start by assuming that we can calculate the Wasserstein distance. What benefits can it bring us? We assume the distance between Pg and P data is d0. In this example, the Wasserstein distance calculated is d0. In this example, the distance between Pg and P data is d1. The calculated Wasserstein distance is d1. We assume that d1 is relatively small, and d0 is relatively large. While calculating the Wasserstein distance, the Wasserstein distance of this case is relatively small, and the Wasserstein distance of this case is relatively large. So, we can know that from left to right, the Wasserstein distance is getting smaller and smaller. So, if you observe the Wasserstein distance, you will know that from left to right, our generator is getting better and better. But, if you observe the discriminator, you will find that you can't observe anything. For a discriminator, the JS divergences calculated here by every cases are all the same. They are all the same good or the same bad. But, if you use the Wasserstein distance, from left to right, we will know that our discriminator, or our generator, is getting better and better. So, by changing the way of calculating divergence, we can solve the possible problems of JS divergence. It reminds me. An evolutionary example. This is the evolution of eyes. The one on the right is the human eye. The human eye is very complicated. Some creatures have very primitive eyes. For example, some cells have the ability to sense light. They can be regarded as the most primitive eyes. But, how do these most primitive eyes become the most complicated eyes? It is actually very difficult for humans to imagine. This is so simple. Just some light-sensitive cells on the skin, via mutation, become some light-sensitive cells. It sounds reasonable. But, how can it possible that mutation from natural selection generates such a complicated organ? How does it generate such a delicate organ of the eyes? Then, if you feel that you can directly jump from this place to this place with one leap, it's not going to happen at all. But, there are actually many continuous steps between them. From light-sensitive cells to eyes, there are actually continuous steps between them. For example, the light-sensitive cells may appear in a relatively concave place. Skin becomes concave. So, the light-sensitive cells can receive light from different angles. Then, it feels that it could cover the concave area. Later on, it feels that, inside the enclosed place, it could fill some liquid. Then, it becomes human eyes in the end. Jumping from here to this step is very large. But, every small step here can increase the chance of a species to survive. And it can make the probability higher for a species to propagate. Since every steps here can increase the probability of a species to propagate, then, species can evolve from the left to the right, to eventually generate complex organs. And, I think that, when you use GAN, when you use this Wasserstein distance, to measure your divergence, you actually created a similar effect. Originally, PG0 is very far away from P data. You want it to run from here to here in one step. One step from here to here. You want these PG0 and P data to align together directly. It is impossible. It may be very difficult. For JS divergence, it needs to jump from this step to this step. And its loss of JS divergence will be different. But for W distance, you just have to move PG closer to P data. And W distance will be changed. W distance will be changed. You can train your generator by minimizing W distance. So that's why, when we change from JS divergence to Wasserstein distance, it can perform better. Okay, when GAN uses Wasserstein distance to replace JS divergence, this GAN is called GAN. The next problem you will encounter is how to calculate Wasserstein distance for P data and PG. How to calculate their Wasserstein distance. Wasserstein distance is a very complicated thing. If I want to calculate Wasserstein distance, I need to solve an optimization problem. How to calculate in practice. I won't talk about the process here. I just tell you the result directly. Solve the following problem of optimization. The value you get is Wasserstein distance. It is the Wasserstein distance of P data and PG. I found that I made a small mistake here. What kind of small mistake is it? The X here may be changed to Y. And it will be more consistent with the previous slides. So the X here in the previous slide is all Y. They all refer to a picture. Okay. They are the outputs of the network, instead of the inputs of the network. Okay, what kind of stuff is in this formula? Let's take a look at this formula. This formula says that if X is from P data, then we have to calculate its expected value of D of X. If X is from PG, we calculate the expected value of D of X, but multiplied by a minus sign. So, if you want to maximize this objective function, what result will you achieve? You will get that if X is sampled from P data, D of X, the output of discriminator, is the larger the better. If X is sampled from PG, sampled from the generator, then D of X, The output of discriminator should be as small as possible. But there is another limitation. It's not just making the value in the braces becomes larger. Another limitation is that d cannot be a random function. D must be a one-Lipschitz function. You may ask, what is one Lipschitz? If you don't know what it is, it doesn't matter. You just think that d must be a sufficiently smooth function. It cannot be a function that changes drastically. It must be a smooth enough function. Why is it so important to be smooth enough? We can understand it intuitively. Assume that this is the distribution of real data. This is the distribution of generated data. If we don't have this restriction, and just look at the value in the braces, the objective here is to maximize these real values. The larger the d of x, the better. Let the generated value, its d of x, to be as small as possible. If you don't make any restrictions, just want a result that the larger the value here, the better. The smaller the value here, the better. The blue dots and the green dots, which are the real image and generated image, do not overlap. What will your discriminator do? It will give the real image an infinite positive value. Give an infinite negative value to the generated image, so your training has no way to converge. You will find that, as long as the two piles of data do not overlap, the values you calculate are all infinite. The maximum value you calculated is infinite. This is not what we want. Isn't this exactly the same as the problem of JS divergence? So, you need to add this restriction. You have to add this restriction. And then your maximum value will be Wasserstein distance. And so it is GAN. Okay, why can the problem be solved? By adding this restriction? Because this restriction tells the discriminator not to change too drastically. It must be smooth enough. When you require your discriminator to be smooth enough, if the real data and the generated data are relatively close, then you can't have a very large real value and a very small generated value. Because if you make the real value very large and the generated value very small, there will be a big gap between them, and the discriminator will change drastically. It will not be smooth. It will not be one Lipschitz. So to make it be one Lipschitz, the value here can't be very large. The value here can't be very small. Then the discrimination will be smooth enough. Intuitively, if real data is far from the generated data, then their values can be quite apart. The value calculated here will be larger. And so will your Wasserstein distance. If real data is close to generated data, even if they don't overlap, because of this limitation, written under max, the limitation imposed by the one Lipschitz function, you will find out that the values actually won't go to infinity. The distance between the value of real data and the value of generated data, due to the limitation of the one Lipschitz function, cannot be too apart. The Wasserstein distance you calculated as a result will be smaller. Okay, the next problem is how to achieve this restriction. How to ensure that the discriminator will meet the criteria of a one Lipschitz function? When GAN was first proposed, there were actually no good ideas. They could only write out this equation, but solving it, that's a little difficult. So the earliest paper on GAN, the earliest paper using Wasserstein, said that it used a rather rough implementation. It simply trains a network. When training the network, its training parameter will be bounded between c and negative c. If it exceeds c, after updated by gradient descent, it is set to c. After gradient descent, if it's less than negative c, just set it to negative c. This method does not necessarily make the discriminator become a one Lipschitz function. You can imagine that maybe this method can make our discriminator relatively smooth, but it didn't really solve this optimization problem. It didn't really make the discriminator meet the restriction. So there are other ideas. One of them is called gradient penalty. Gradient penalty is from a paper called Improved GAN. The paper says, assuming this is the distribution of your real data, and this is the distribution of your fake data, I will take a sample from the real data, and take a sample from the fake data. Then, take another sample between the 2 points. The gradient of this point should be close to 1. You might wonder what it is talking about. What is the relationship between this method and this restriction? You can see the paper Improved GAN for more details. I think for now, you don't really have to focus on the relationship between gradient penalty and this restriction, because there are many more other methods to solve this problem. In fact, after Improved GAN, there's an Improved GAN. This paper really exists. It modified this restriction slightly. There really is another paper called Improved GAN. There's another method to restrict D to be a 1 Lipschitz function. This is called spectral normalization. I will put its paper here for your reference. If you want to train a very good GAN, you may need to use spectral normalization.